You know that moment when you're standing in the kitchen waiting for a pot of water to boil and you just kind of watch it? It's something we do all the time, right? But what if I told you that inside that super simple everyday act, there's a pretty profound scientific principle at play? Well, today we're going to take that kitchen scene and turn it into a deep dive into the world of thermodynamics. It all kicks off with a simple question. Picture this. A young girl named Priya is making tea, watching the pot, and she sees those little bubbles starting to form on the bottom. So she turns to her dad and just asks, why? And that one simple question, well, that's the key that's going to unlock everything we're about to get into. Okay, so to answer Priya's question, we have to zoom in, way, way in. We're going past the pot, past the water itself, all the way down to the microscopic level. Because the real secret to boiling water isn't just about making it hot. It's about what all that heat is doing to the trillions and trillions of tiny water molecules that are zipping around in there. So first things first, we got to be clear on what heat actually is. When you turn on your stove, you're not just, making the burner hot. You are supplying energy. That flame or that glowing red coil, it's like a power station, and it's pumping energy directly into the water. Right, so as that energy flows into the pot, all those individual water molecules, they just soak it up. And what do they do with all this new energy? They start to move. They vibrate, they zip around, they bump into each other way, way faster. It's like a totally calm room slowly turning into a wild, frantic dance party. That is literally what is happening inside your pot. So the molecules are moving faster and faster, and this dance party is getting more and more intense. But it can't just go on forever. As the energy level keeps climbing and climbing, the water starts to approach this critical threshold, a real point of no return where everything is about to change. And that critical threshold? It's 100 degrees Celsius or 212 degrees Fahrenheit if you prefer. Now, this isn't just some random number. For water, at sea level anyway, it is the magic number. It's the exact temperature where the molecules have absorbed so much energy that they are right on the edge of a massive transformation. The boiling point is basically the temperature where liquid water finally has enough energy to make its great escape. The molecules literally start breaking free from being a liquid and turn into a gas, which, of course, we know is steam. And those bubbles that Priya saw? Yep, that's it. That's the beginning of the escape. But hang on, because this is where things get really, really interesting. So we've hit 100 degrees, the water is boiling like crazy, but something really weird is happening with the temperature. Seriously, think about it. The stove is still on full blast, pumping heat into that pot. But if you were to stick a thermometer into that boiling water, it would not go past 100 degrees Celsius. It just stops. So where is all that extra energy going? This is the big paradox at the very heart of boiling. And the answer is this amazing concept called latent heat of vaporization. It turns out all that extra energy from the stove, it's not making the molecules move any faster anymore. Nope. Instead, it's being used for a totally different job. It's being used to physically break the bonds that hold the water molecules together as a liquid. That's what lets them transform into a gas. It's like hidden energy, doing hidden work. So you can really think of it in two separate phases. First, you have the heating phase. All the energy's job is to make the molecules move faster and raise the temperature. But then, phase two, boiling. The temperature completely flatlines at 100 degrees because now all that energy is dedicated to one single mission, breaking those bonds and turning the liquid into steam. Okay, so we've gone from a simple pot of water all the way down to the molecular level. And in the process, we've uncovered a fundamental law of physics. But what's so incredible is that this idea, this principle, it's not just stuck in our kitchens. It scales up, way up, and it governs these massive systems all around us. That hidden energy we talked about, the energy tucked away in steam, it is incredibly powerful. It's the reason steam cooks food so fast. It transfers a huge amount of energy when it hits your food and turns back into water. And on a much, much bigger scale, this exact same principle is what powered the steam engines of the Industrial Revolution, and it's still how we generate a ton of our electricity today. And that, right there, brings us full circle. We started with Priya just watching bubbles form while making some tea, and from there we unraveled a core concept in thermodynamics. It just goes to show you, sometimes the most profound truths about how the universe works are hiding in plain sight, just waiting for a curious mind to ask a simple question. So, the next time you're in your kitchen, or really just looking at the world around you, maybe take an extra second and ask why.
What other simple, everyday things that we take for granted might secretly be governed by these powerful, elegant laws of physics? The answers, I promise you, are everywhere.